thanks, Luke, for the introduction. So today I'm going to present some work I did with Luke on the multi-scale modeling of the ocean surface turbulent mixing using coupled MPAS-Ocean and PALM. So I would like to start from this background image. So this is one of the my favorite pictures. This is showing a bloom of cyanobacteria in the Baltic Sea, and the structure you see is the abandoned structures in the ocean. And you can see in the detailed box here, you can see clearly it's an eddy, but on top of that, you see much finer structures that looks like laminar cells. So this is a nice illustration of the multi-scale nature of the ocean physical processes. So I like it very much. So why do we care about ocean turbulent mixing? So on the large scale side, so the ocean absorbs a great amount of excess heat and CO2 from the atmosphere. We know that it takes like a quarter of the anthropogenic CO2, and about 90% of the total warming is in the climate system. And the ocean turbulent mixing affects the distribution of the absorbed heat and CO2, and therefore the capability of the ocean to buffer the climate change. On the smaller scale, ocean turbulent mixing affects the transport and dispersion of the ocean pollutant, such as spilled oil and plastic waste. And it's also affect the availability of nutrients for the biogeochemical processes, as well as the sediment transport in an estuarine environment. So we know that the ocean turbulent mixing is small-scale processes, and it's not resolved in the ocean general circulation models or Earth system models. So they have to be their effects have to be parameterized. So there are quite significant discrepancies among many of the ocean turbulent mixing parameterizations, like shown in this figure. I won't go into detail, but this is some metric of showing the differences between 11 ocean surface vertical mixing parameterizations, and you can see there's a large spread. So, and also large eddy simulations are given the lack of direct measurements. Large eddy simulations are usually used to develop and validate the ocean turbulent mixing parameterizations, and I'll also use this tool in this work. So why do we care about multi-scale modeling? So we know, as shown in this figure I talked about before, the ocean mixing is multi-scale. So on the smaller side, there's like the boundary layer turbulence. It's on the order of a meter. And also the sub-mesoscale eddies and fronts, it's on the order of a kilometer. And to the large scale, we have the mesoscale eddies, which is about like 10 to 100 kilometers. And we know that the interactions between these processes matter for the ocean mixing. And also the simulations that resolve all these important physical processes are extremely computationally expensive. And also in this work, I would like to combine the flexibility of mesh resolution in MPAS-Ocean and the turbulent resolving LAS to explore a way to do the multi-scale modeling of the ocean turbulent mixing. So in the rest of the talk, I'm going to first introduce this multi-scale modeling framework. It's basically coupling MPAS-Ocean with an turbulence resolving large eddy simulation, PALM. And I will also talk about porting PALM on GPU to reduce the computational cost. And I'll briefly talk about two test cases for the evaluation, an idealized diurnal cycle test and a mixed layer EDDY test. And then I'll talk about some pathways to move forward. So, so the scale modeling, I think for this audience, I won't need to talk too much about this MPAS-Ocean model. So we solve the large scale dynamics in MPAS-Ocean. So it's basically an ocean general circulation model. It's solve the hydrostatic, incompressible, and Bosnisk primitive equations on an unstructured mesh using finite volume discretizations. For the small scale dynamics, I'm going to use this turbulence resolving larger simulation model, PALM, and it basically solves the non-hydrostatic, incompressible, and spatially filtered Navier-Stokes equations with Bosnisk approximations on a Cartesian grid using finite difference discretizations. And to couple these two, basically embedding PALM inside some grid cells of MPAS-Ocean. So to look at closer, basically this is some idealized mesh of MPAS-Ocean. So I'm going to embed an PALM simulation inside one MPAS-Ocean grid cell. So here we have the flexibility to run PALM only on selected MPAS grid cells. I'm going to talk about it more later. And on other grid cells, I'm going to use the standard KPP, K-profile parameterizations for the vertical mixing. And I just want to mention here that the coupling for the tracers is straightforward because PALM is on the cell center and all the tracers of MPAS-Oceans is also on the cell centers. But for the momentum, it is a little bit tricky because for MPAS-Ocean, the velocity is on the cell edges. It might cause some inconsistencies that I'll talk about later. For the coupling in time, so I'm going to run MPAS-Ocean alongside with the PALM. So this is an illustration of the coupling for one MPAS grid cell. So basically they are running together and we exchange the information at each MPAS-Ocean time step by including this, because we want to make sure the momentum and tracers are consistent in MPAS-Ocean and PALM. So we need to exchange information between them two by exchanging by including a small scale forcing term in the MPAS-Ocean dynamics and a large scale forcing in the PALM dynamics. So for the small scale forcing, it's straightforward because this basically represents the vertical mixing. So it's the divergence, vertical convergence of the fluxes. And for the large scale forcing, we actually have multiple choices. We can choose different processes we want to represent, but to start, I'm going to use a very simple one. It's basically a relaxing term. So we relax the smaller scale tracers and momentum to the large scale with a flexible relaxation time. So we want to explore how tight we need for these coupling. Okay, so because running PALM, because it's still a three-dimensional large eddy simulation, running it in MPAS-Ocean is still computationally very expensive. So we want to port PALM on GPU as part of this exploration. So PALM is ported on GPU using the OpenACC. and CUDA fast Fourier transform library. So we are benchmarking the speed up on two machines. Basically, the first is a Linux workstation with some state-of-the-art, hardware, and also I'm going to benchmark it on Summit. So here I define the speed up factor as the runtime with one CPU over the runtime with one CPU plus one GPU, always one MPI task. Although this is not a fair comparison or fair measure of the speed up for using GPU, but I find this measure is useful for our purpose. So here is the speed up. So I plot the speed up factor against the size of the problem. Basically, it's the mesh size. And we have solid curves for benchmark on Summit and dashed curve on Linux workstation. So here, different colors represent so the black one is the total, and different colors represent the three most computationally expensive subroutines in POM. So you can see that depending on the work, you can have different speed up, but overall you can get like 10 to 16 times speed up depending on the size of your problem. So it's being slowed down by the pressure solver, which use the fast Fourier transform. So I'm going to test this in two simple test cases. The first one is an idealized diurnal cycle. So this is basically a single column simulation, but in MPAS-Ocean, single columns means we have to use 16 columns, like shown in this diagram. So this is an idealized diurnal heating plus constant cooling. So the sum. So if you integrate the heating over a diurnal cycle, it goes to 0. And then we have constant wind stress and rotation. So here is an illustration of what, in this test case, what a standalone POM and KBP will give us. So so this is showing the temperature, zonal velocity, meridional velocity. So I'm going to focus on the vertical profile. So this is taken at the time where the sea surface temperature reaches maximum due to the diurnal heating. So I'm going to look at these vertical profiles of temperature, velocity, and I'm going to try to test the sensitivity of these simulation results with different coupling strategy. So here the solid curve is the standalone POM, and dashed curve is the standalone KBP. Okay, so I'm going to zoom in these vertical profiles. So if we do, say, because these profiles are the standalone POM and KBP, and we want to compare the coupled POM and MPAS-Ocean with these profiles. So if we run POM on all these 16 cells with the same forcing, I got this blue curve, which is close to the standalone POM, and this is expected because in this test case, running POM on all 16 cells is basically very, very similar to a standalone POM because there's no large-scale forcing in this single column setup. So if we start to couple, so if we only run POM on this single cell, the sixth cell, and we only couple the tracers, So we see, as expected, the tracers match the palm very well, but the momentum, the velocities, you see quite some differences. This is because as I mentioned before, the MPAS-Ocean velocities are on the cell edges. So these output are actually interpolated from these 6 edges. So that kind of account for the impact of the neighboring cells, which use KPP. So you see it resembles the KPP profile more than the palm profile. And you can try different tightness, different levels of tightness of coupling the momentum by adjusting the relaxation time. So as the coupling become tighter, you start to see this surface warm layer develop. This is represents some like artificial influence from the neighboring KPP cells. So this is an issue we are going to, going to address like in future work. But here, by using like a loose coupling, using the coupling relaxation time of 5 hours, we kind of reduce this effect. And also here, I'm showing the surface temperature and the velocity differences, like the neighboring. Remember, all the 15 cells are using KPP, whereas the 6th cell is using palm. So you see that there are some differences among these cells. But I guess this is one of the future work we'll need to address how we combine these two using different representation of the vertical mixing. So the second simple test case is a mixed layer test case, mixed layer eddy test case. So we want to look at the turbulent mixing in the presence of large scale forcing due to mixed layer eddies. So the setup is simple. It's a warm filament, like showing in the figure here, the temperature distribution. And we start from 0 velocity. And this domain is doubly periodic, and there's no surface heating or cooling, and the surface forced by constant wind stress, and there is rotation. So because there's wind and rotation, we expect there's a Ekman transport. So you will have you expect this warm filament to move to the left. And then you will get a stable front where you have warm water move over cold water, and on the other side you have an unstable front where you have cold water moving on top of the warm water. So if we run this, spin up this simulation with KPP for 15 days, we kind of see a mixed layer eddy develops here. So note that the unstable front is moved from here to moved to here, and whereas the stable front move outside the domain and come back on the other side. So starting from this, we did 3 simulations with different configurations. One is we continue with KPP. The other is we run palm on these 8 grid cells with 2-way coupling. The third one is just a reference. We are running palm on these 8 cells without coupling. So to illustrate the results, I'm going to focus on these 4 locations, which is on both sides of the unstable front and both sides of the stable front. So here is the time evolution of the temperature profiles at the 4 locations. So horizontal is time, vertical is depth. So basically, you see that, for example, if you first look at the uncoupled palm simulation, so this is basically just doing large simulation forced by constant wind stress. So there's no interesting features here. This is expected because this is a very simple case. But if you look at these two columns, the KBP column and coupled PALM and MPAS-Ocean, you see some interesting structures in the temperature distribution. So this is represent the mixing due to large-scale forcing. Here, the mixed-layer eddies plus the vertical mixing, vertical wind-driven mixing. So you see some the results are similar between KBP and PALM, suggesting that in this case, the large-scale forcing are dominating the results here. But you see some differences that suggests that the different representation of the turbulent mixing can potentially affect the large-scale, like the temperature evolution, and maybe affect the mixed layer evolution of mixed layer eddies. So here is basically the same figures for the velocities, and you see similar structures. I won't go into details for and also you can even look closer to the turbulence statistics. Here is an example of the buoyancy fluxes. So you see much stronger differences between like the runs with KPP and runs with PALM. So that suggests that really the different representation of the turbulent mixing can actually affect the evolution of the buoyancy in these cases, and it potentially can affect the evolution of the large scale forcing the mixed layer eddies if we use PALM on all the grid cells. So again, these are very simple test cases. This is just an illustration of demonstration of the frame coupled MPAS-Ocean and PALM work as expected, but we can have much more applications of this framework in the future using with different, more complex test cases. So to summarize, so here we are building towards a multi-scale modeling framework to study the ocean surface turbulent mixing and their interactions with large-scale processes. So we have choose a flexible coupling strategy between MPAS-Ocean and PALM. This is different from the traditional superparameterization approach. And we think this flexible coupling strategy is useful for, at least for exploration of how should we couple the large scale dynamics and the small scale dynamics. And here we port PALM on GPU and achieved over 10 times speed up. And we demonstrate the framework with two simple test cases. The goal is first to evaluate the functionality of the coupling framework. The second is also to expose potential issues for future work. So moving forward, the most straightforward step forward is to include the lateral gradient in the coupling. So because for the large scale forcing term, I said before that we are using a very simple relaxing term right now, but it is just one step forward to look to include the large scale lateral gradient term, which will allow more physics, for example, the baroclinic instability and symmetric instabilities in the small scale dynamics. And we can use this framework to do focused process study of ocean turbulent mixing in the presence of large scale processes. So for example, we can run PALM on the finest grid cell of MPAS-Ocean in some regions of interest. And we can also use this framework to explore parameter space for better parameterizations. So we can run larger simulations of ocean turbulent mixing under various forcing conditions with and without large-scale forcing, for example, under hurricane conditions. And we can also explore the possibilities of improving the simulation results of GCM by having high fidelity representation of the turbulent mixing at only a few locations, not all. So so this work is right now in review in geoscientific model development. If you want to know more, please stay tuned. And with that, I want to stop here and take any questions.